physical, see how much they weigh.
Oh, yeah. Yeah. Alright, let's start out with something, a little bit review. It has quite a bit of stuff on it that we can talk about.
It's the rabbit blue. Are like these two lessons mostly like vocab and conception?
Yeah, probably.
Yeah. Homework. That's two months. There's that just now. It's math.
Okay.
There's no math in here, so I was asking.
Alright. Heat curve for water. Okay. There's quite a few things we could put on here. Quite a few things we could talk about. There's a lot of information up here that we might not initially think about. But do you guys remember sensible heat versus latent heat and what the difference is?
Temperature and when the thing goes up, that's
So it's at the temperature change.
Latent heat is a straight line. It's energy is being absorbed to change the state.
So Emily stated kind of, specifically what I'm looking for. Sensible heat is the heat that makes sense. When you heat something up, you notice a temperature change. Latent heat is when you're going through a phase change and what does not change.
Temperature.
Okay, we can talk about what phases we have at each of these given points. What phase do we have here?
Oh, yeah, solid.
What phases do we have there?
Melting.
Phase.
Solid and liquid. That's melting.
We have both. At that point?
Well, it's in the process of melting, so yes.
Yeah, you can have both. Okay? How about here?
Is this one Celsius?
Here?
That one, that'd be gas, liquid gas, vaporization.
And here?
Gas. Further, you got some plasma too. That's a weird thing.
I don't know where the plasma point is.
Yeah, it's really weird.
Okay?
I don't even know if we can make plasma.
There's quite a few other things we actually could discuss. This point and this point have a couple names.
somewhere out of it.
Maybe you tell me about that location. Specifically talking about energy. The length of that line is going to be dependent on something. Maybe I should ask this one. It's in your notes.
It's
The boiling point.
It is the boiling point. You could say that. Yeah, that's one thing you could say. You could say boiling point, or where it condenses. Can you say condensation point? I never really thought about that, but
the opposite.
yeah, which is what that would be. Then you could then say here is your melting slash freezing point. But I'm looking for one other thing on here for those two locations. Close, right idea, wrong point. No, that doesn't change them. No. If we're talking about here and here and here, specific heat capacity, yes, definitely.
So it would be what the strength.
Okay, so I'm going from a solid to a liquid or a liquid to a solid, right? Okay, that's going to take a certain amount of energy. That energy has a name. Nope. We talked about it yesterday or 2 days ago. Enthalpy of vaporization. Here would be the change of H of vaporization. We didn't necessarily talk about this point yesterday, but it is the change of H of, do you remember from chapter 5? 6.
Solidification.
Starts with an F.
Formation.
That's right. Okay, great. You got the change in H of vaporization and the change of H of fusion. What does that mean? What? Needed to what? Yeah, to go from one phase to the next. All right, we talked about how, well, it was this chapter where we talked about the difference between the change of H of vaporization and the change of H to break the bonds, right? Remember we talked about how it was like 40.9 kilojoules per mole was your change of H of vaporization, and then it was like 936 or something like that kilojoules per mole needed to, break the bonds. And we talked about how intermolecular forces and intramolecular forces here we're breaking what? What type of forces? Inter or intra? Intra. And here we're breaking intermolecular forces. And we talked about how intermolecular forces are significantly weaker. Okay, and that shows up with how much energy you would need to break the two. Okay? So the length of this is going to be dependent upon how much energy would be required to break the intermolecular forces. So if I had a horizontal region here that was longer, what would that suggest? It would take more energy to break the intermolecular forces, and it would tell you that they are stronger. Okay? Then, Ryland started to allude to specific heat capacity. Again, I know I don't really need to be talking about this now, but it appears that we do need some more review. Okay? We could talk about specific heat capacities. at each of these locations. And if you remember, what is the definition of specific heat capacity?
How much energy it takes to raise a gram of substance 1 degree Celsius.
Okay, it would make sense why that would go with the sensible heat, right?
Yeah, it does.
Why?
Just raising the degree Celsius.
Yeah, you're raising the temperature. You wouldn't talk about specific heat during a phase change because what doesn't happen during a phase change? The temperature doesn't change.
So really, specific heat during a phase change is really high until it finishes phase change.
Infinite?
Yeah, it's infinite. Well, it might speed up the process of the phase change, wouldn't it? The more energy you put
No, I don't.
like you're melting ice, no matter how hot.
I don't know.
Melting ice, like throwing in a volcano versus setting on a sidewalk, it'll melt faster than the volcano. They have more energy to put more into it at once.
Yeah, but that doesn't affect specific heat.
It does, you're right. How much energy, I don't know.
Regardless of whether you throw a piece of ice cube in a volcano or you plop it in your mouth,
Yeah.
it's still going to save the same amount of energy to
Yeah.
change the temperature. It's just going to happen a lot more quicker
Yeah.
in a volcano, I
That's what I was
guess.
thinking, but you're right, it doesn't have to.
Okay, so when we talked about how specific heat capacity is these locations. Okay, what would a changing specific heat capacity do to those lines?
You decrease specific heat to make the whole thing shorter.
No.
All
Oh yeah, make it a steeper slope.
Steeper, right? Lower specific heat would make it steeper lines. Why?
Because the rate changes.
Yeah, right? The temperature change is going to happen a lot faster when you don't need as much energy to change the temperature.
Like metal versus snow. I think they're right. It doesn't melt very easily, it's like a random thing.
Picture water pretty like water.
Yes, absolutely. The specific heat for water is like 4.18. Metal is like 0.21. Depending on the metal, I just threw out a random number. Okay, and that's another reason why we talked a few days ago about how water is a great absorber of energy, so that our Earth is not significantly heating up and causing problems with a whole variety of things. And I'm trying to think if there's anything else we could talk about what those lines. I mean, when we do a graph, it's a model. It's used to describe something and explain something. It's not just a fancy picture. Okay? So we've seen this heating curve before, but we can break this down a lot more at this level than you guys ever could as a physical science student or as a, even a regular chemistry student. Okay? All right, I think that's good for that. Any questions on that? Talking about vapor pressure. We're going to talk theory here again. Fun theory stuff. And maybe I could have elaborated a little bit more about intermolecular forces relating to what that would look like on a heating curve. Open up your books. We're going to talk about a few cases. I wish I need to get one of these apparatus. It's 477. So we've talked about vapor pressure. What is vapor pressure?
The pressure of the condensed
It's a pressure caused by the gas molecules above a liquid, right?
Okay. Yes. But solid has a vapor pressure too?
Yeah.
So is it weird to think about that solids evaporate?
Is that why, like in a freezer, if you open an ice cube, that there's a little fog sometimes in the freezer? Or no? Maybe that's just different. Maybe not. Maybe that's just
That was condensate.
that would be kind of nice.
Yeah,
That's
no.
probably just the moist air cooling, probably, if you open the door.
Yeah, I don't know. I mean, that would be like similar to walking outside and seeing
Yeah.
your air, when you breathe, seeing your.
Isn't that, it's just the moisture from your breath condensing in the air to make bigger droplets.
What's the matter?
I asked her if she looked good, she did.
Has she? Still haven't?
I just re-signed up.
You just what?
Just signed up again.
For another ACT?
Yeah.
Why would
You didn't even look and
I
you.
don't want to.
Did you just feel you did bad?
Yeah, I don't.
Like worse than you did? Was that the first time?
Yeah. So maybe you think you did
You take it again, and then you go back and you realize, oh, I got a 36. I didn't need to take that again. Why am I taking that again?
I should take it again. I didn't do very well in the science section.
That would be the time.
Right when I've been reminded of science.
Yeah.
that. How'd you do on math?
Average. I ran out of time in both math and science. In like the last 5 questions, I just answered randomly because I didn't have time to fit to the math. Yeah, I work too slow.
Yeah. That's why I find that the kids that process quickly do better on the ACT. But if you took time out of it, there would be some kids who would get higher ACT scores than those that can process quickly. But that's why I would be an advocate of a timed ACT and an untimed ACT.
Yeah, like you have to look at both parts.
Yeah.
Because some jobs you need to be able to work quickly for math.
Absolutely.
But some jobs you don't need to.
Yeah.
So it shouldn't. Yeah.
Anyways. All right, so looking at this, there's a little visual in the top left corner, a little table, okay? And believe it or not, there is a vapor pressure that solids have. And you can kind of see, you can see the vapor pressure line for the liquid, and you can see the vapor pressure line for the solid, and you can kind of see, if you look at your X and Y axis, you can kind of see it's pressure over what?
Temperature?
Temperature, okay? And notice that you've got the green line representing your vapor pressure for your liquid, and what is that, like an orange or yellow line representing your vapor pressure for solid. What can you make from that? Just looking at that, looking at your X and Y axis, anything you can do is from looking at that graph.
When the solid is warmed up a little bit, it has greater vapor pressure than the liquid.
There's a point where the solid vapor pressure is greater than the liquid vapor pressure,
Yeah.
right?
From like what, 0.2 plus plus 2 and onwards, it's like, it's higher. Maybe plus 1 and onwards. Yeah, plus 1 and onwards.
Well, look at, do you think there's any significance to where those two vapor pressures equal? Where are they equal?
Oh, just past 0. Well, maybe at 0.
Yeah, it's supposed to be at 0. Well, what happens at 0?
Freezing and melting.
Freezing and melting. Okay, so that's a pretty significant thing, that when freezing and melting occurs, it happens when their vapor pressures equal. Okay, so then how do you know if I'm freezing, or how do I know if I'm going to melt? Well, that depends upon whether you're adding energy or removing energy. Okay, so if you look at the very bottom, what you have is an apparatus where you have on one side you have the solid phase, and on the other side you have a liquid phase, and it's closed to the outside atmosphere. Okay, so you can have vapor that gets created from both the solid and the liquid. So we're going to talk about kind of 3 cases of whether it will melt, whether it will freeze, why it melts, why it freezes. And what's interesting about this, and it might be kind of goofy, it was goofy when I first read it and learned it, was that, believe it or not, supposedly, things melt, when things freeze, they happen through the gaseous phase. What I mean by that is when something melts, the solid gives off vapor, and then the liquid absorbs that vapor. So essentially, what happens is when you go from a solid to a liquid, it happens through the gas phase. Mind blown. Okay, so let's kind of go through case 1 here, and let me describe what I mean. Okay? It says a temperature at which the vapor pressure of the solid is greater than the vapor pressure of the liquid. Okay? At this temperature, the solid would require higher pressure than the liquid does to be in equilibrium with the vapor. So let me try to draw this picture because it's kind of hard to see. You know, you can't see the working parts going on here. I want to kind of make this a simpler. Graph. So we'll say we have ice and liquid. I should just say solid liquid. Okay, what are our conditions again? It says vapor pressure of the solid is greater. And the liquid, the vapor pressure is lower. Okay, so from what we know, this would be a temperature above 0 degrees or below 0 degrees. What do you think? It's going to be above, and I'll explain why.
It needs more pressure in order to.
And you can, if you look at your chart here or your table at the top, okay, where would you see the solid vapor pressure higher than the liquid vapor pressure? If you just look at that table, above 0 or below 0? The solid vapor pressure being higher, above. Okay, so melting is going to happen in this case, and let me explain how this works. Okay. Well, there is an equilibrium that the solid ice is trying to reach with its vapor. Okay? So what happens is the solid is saying, I need more vapor in the air to reach equilibrium. Does that make sense? So it's starting to evaporate particles so that the vapor, the pressure that the vapor has in here is at equilibrium with with the solid form. Does that make sense? Okay, so it starts to shoot out gas molecules so that it can reach equilibrium with the vapor above it and the solid that it's in. Okay? Well, at the same time, the liquid is trying to do what? Does it want a high vapor pressure? No, so as the solid starts to give off the vapor, the liquid is starting to say, no, that's not what I want. I want to reach equilibrium at low vapor pressure. So what ends up happening is, as it starts giving off gas particles, right, the pressure starts to increase. And the liquid says, whoa, I don't want that high pressure. Okay, I want low pressure. So how would the liquid lower the vapor pressure? Take the molecules. So what ends up happening is that as the solid's giving off vapor, the liquid is absorbing it, or taking it in. And so what ends up happening is that the solid melts through the gaseous phase. That's why I want to get one of these apparatuses, because it would be, to me, it would be weird to see solid slowly going bye-bye, but not seeing liquid in the bottom here.
So that works with most.
Wouldn't that be weird?
So that works with any substance. How do you keep this solid? How do you keep the ice like cold though?
Well, I bet like.
Eventually it'll melt.
Yeah, it would melt. But what I'm saying is, when it melts, we're used to seeing when you have ice in a glass at room temperature. We're used to seeing it melt and stay in the glass, right?
Well, but normally it wouldn't have anywhere to go. They'd just go straight up and then fall back down.
Well,
Or
yes, but the big key here is in this situation, it's enclosed to the atmosphere. So when you're doing it in the atmosphere, you've got the atmosphere that's keeping it all in, and so actually it's happening like, I don't know if it's like a pocket, like a little bubble that gets created between the atmosphere, and I'm not exactly sure.
Because like the cold air is denser than the normal air, right? 'Cause it's
I mean, that would make sense. I didn't really
it's
think
going to
about
be
that.
forced back into the top, right?
And remember, this could be completely theoretical.
Yeah.
You know, but they're creating a theory based on what they've seen from vapor pressures and things along the and from experiments like this, where they notice if you keep it enclosed to the atmosphere, the solid evaporates. Right? If it's evaporating, it's not melting and creating liquid at the bottom, right? It's going into the air. It's being transferred to the liquid. So at the end, when we're above 0 degrees, you should have no solid left and no liquid in the bottom here, and the liquid should have risen, right? It's a little crazy.
Could you do it with any substance though, theoretically? If you could somehow make the temperature.
Yeah. We're using water because we're most familiar with water,
Yeah,
but this would
you
happen
could,
for
like-
every substance.
Yeah, you have the temperature.
So is this
but-
water or no?
That's water. Yep.
So how is it still solid over?
It's not. I'm saying, well, you can have, if you take ice out of a freezer and put it in, it takes time for it to go.
So it's gonna go up and then once it's all melted, it's gonna
No, it's never, so when you're above 0 degrees, it's never going to reach the vapor it would need to stay as a solid, and that's why it changes to a liquid. Because it can never reach equilibrium in the solid form above 0 degrees. It can't. The only way it can reach equilibrium is if it transfers to what? The liquid phase.
So, is that why if leave something uncovered in a freezer, it kind of goes weird? Like if the ice cream uncovered in a freezer, like if it's freezing.
Like freezer burn, I don't
Well, it
know.
loses its water. Like have you ever had ice cream that's gotten frozen too long?
Yes, it tastes
And
nasty.
it's like it's foamy and it doesn't have water in it. Is that what it is?
It's possible. Again,
Okay.
I don't know for sure. Again, we're talking a lot of possibilities. Yeah. Okay. So then, you can imagine what's going to happen then if we are below 0 degrees.
The opposite.
Yeah. What you would have, if you look at your chart, if you're below 0 degrees, okay, your vapor pressure for liquid is greater. And so you would have the opposite happening. Your liquid vapor pressure is now high, and your solid vapor pressure is now low. And so again, what ends up happening now is the liquid is trying to make the vapor pressure higher by evaporating. And the solid says, I don't want the vapor pressure to be high because I'm trying to reach equilibrium, so it absorbs and forms a solid. So you have the exact opposite going on in this case, where all the liquid would go bye-bye and the ice would increase.
Why wouldn't it just freeze where it was?
Well, it would freeze where it was if it didn't have to go through the gas phase to do it.
Okay. It does.
At least that's my understanding of what happens. Okay? If it didn't have to go through the gas phase, yeah, you would expect the solid to just melt, you know. But remember, this isn't a normal situation, right? We are completely bypassing atmospheric pressure because that's going to change things, right? We're not used to seeing it in a vacuum. If that makes sense.
So this is going to be in a vacuum then?
Yeah, I would assume so. I mean, I don't think it states. There would be no other way to. Or at least low enough atmospheric pressure that it isn't gonna.
Or even wind blowing around too.
So, all right. So what happens if we're like at the melting point? Because if we're at the melting point, how are we going to? Is it gonna melt or is it gonna freeze? Right? Because at 0 degrees, the vapor pressures are what? They're equal. So technically, they both are in equilibrium. So are you going to melt or are you going to freeze? So what's going to happen in that case?
In the direction of the energy.
Yes. Because it's pretty unlikely, or it's probably possible, but it's not easy to do, to maintain 0 degrees perfectly without having energy going in or coming out. Okay? So the reason why we don't see just water and ice remaining water and ice for long, long periods of time is because it's not likely that we can maintain that perfect 0 degrees. There's always either energy coming in or energy going out. So, I mean, if you think about our heating curve, right, there's a period where the temperature doesn't change, right? And whether or not I'm going that direction or I'm going that direction is going to tell me whether or not it is going to melt or whether it is going to freeze. Okay? So if we're above 0 degrees, we know it's going to melt. If we're below 0 degrees, we know it's going to freeze. If we're at 0 degrees, it depends on what? Yeah, energy going in or energy coming out. Okay? To me, this kind of blew my mind when I first kind of understood this idea that things melt and freeze through the gaseous phase. But it makes sense because we can't see the gas, and under regular conditions, we have atmospheric pressure involved, and that's going to change a few things. Right? I think that's it. Oh, a few other things. There's just some vocab words here. Okay, so if you flip the page, 478, there's a few vocab words. We got normal boiling point, we have normal melting point, we have supercooling and superheating. Normal melting point and normal boiling point are pretty self-explanatory. When they say normal boiling point, they're assuming the boiling point that you would normally have under certain conditions. What conditions do you think that's referring to?
STP. Well, air temperature.
No, it's good guess though. It's referring to sea level conditions.
Yeah, atmospheric.
Yeah, constant atmospheric pressure of about 1. And 1 atmospheric pressure would be about sea level. I don't know, plus or minus a few small points, 0.001 or something like that, I'm not sure, but. Okay, so the normal melting point of water would be what? 273 Kelvin, or you can just say Celsius. It's easier at this point.
Kelvin is not what I meant to say.
Yeah, it's not possible.
That's frozen.
Yeah, yeah, it would, and maybe
Like black holes.
yeah. Anyways, we can get into that. That's a whole theory. But anyways, so 0 degrees Celsius is your normal melting point, and your normal boiling point of water would be simply just what? 100 degrees Celsius. Yes. Okay. So why does it have a specific normal? So does that infer or imply that it could be a different boiling point?
Yeah.
Okay, what would change that?
Pressure.
A change in atmospheric pressure, and in what situations would we have changing atmosphere? I mean, technically, guys, even at sea level, we have slight changes in atmospheric pressure. Okay, you could boil water today, check the temperature. It's probably not going to boil at 100 degrees perfectly. And then you could boil water, 5 days from now, and it's probably not going to be the exact same temperature because of the slight change in your barometric pressure, okay, or your atmospheric pressure. Okay. But changing in altitudes is where you have a significant change in your atmospheric pressure, and that would change your boiling point. Okay, last 2 things here, supercooling, superheating. So if you look at the bottom visual on 473, okay, right,
478.
what did I say? 478, yeah, sorry, well, I don't know why I said 473. Let's see if I can find this picture. I know we did it, and it seemed like a silly lab when we did it in chemistry. I don't know if you guys remember the lab where we just essentially froze water and then melted water, and we just made a temperature curve with that. Do you remember doing that, lab?
I do.
A couple years ago, maybe. I don't know. I know for sure you guys did it. I don't know if we did it if we had the technology 2 years ago to do it. But the graph looked like this, where it kind of looks like a heating curve, doesn't it? Because it is really a portion of it. Okay. So what we did here is we had some liquid water, and we put it in a ice bath. We put salt in it, and we'll talk later how adding a solute to water lowers the freezing point. So it actually allowed the water to be colder than 0 degrees so that we could freeze the water in a test tube.
So, do all solutes make it?
Yes, we'll talk about that.
Is
We'll
there
talk-
any way of freezing it? With like adding stuff?
No, not the freezing point or melting point. You can elevate the boiling point
Oh, okay.
by doing that, but yeah. And then that has to do with vapor pressures too, which that's a whole nother, I don't know, that must be coming soon. It's gotta be coming soon. So what happened is if you look on our chart, we actually dipped below 0 degrees.
Oh, yeah.
You see that? It dipped below 0 degrees, then went back up to 0 degrees, and then what happened?
Stay still for a while.
Yeah, which means it was doing what when it was staying still here?
Freezing.
It was freezing. Okay, so actually it got below 0 degrees, went back up to 0 degrees, and then froze. Okay, so what's happening?
Was it just organizing itself?
Yeah.
Like super
Yeah, so supercooling is if you cool it quickly enough or too quickly, those particles have not oriented themselves in the correct shape to form that solid. And so there's a small time frame where they're trying to get in the right spots to form a solid where the the temperature actually cools. What I find fascinating though is that it goes back up to 0 degrees to melt.
Yeah.
That's the thing I find most fascinating about that graph is why it has to go back up to 0 degrees to actually not melt, to freeze. So.
Have you ever watched YouTube videos of super cold water?
So superheating. Oh, I do want to quickly talk about superheating. Superheating is kind of it's the same process, but going to boiling, right?
Yes.
And I actually did this quite often in the lab when I worked in the lab. What if you heat up too quickly? In fact, we didn't necessarily heat up too quickly, but we removed all the atmospheric pressure, which was vacuum, and actually you could boil water at like 20 degrees Fahrenheit.
Yeah.
Not 20 degrees Fahrenheit, 20 degrees Celsius. That'd be cool.
Still.
You can actually boil water. Well, when you do that, when you superheat something or use a vacuum, what ends up happening is that gas, for things to boil, you have to have a bunch of particles come together to form those gas pockets. If it happens so quickly that it actually like jolts or forms a gas so quickly that it's called bumping. And what ends up happening is it like expands so quickly that it like pushes the water up.
Yeah.
And it like bubbles and shoots water everywhere.
I seen a video of that. It's like he gets some container, he microwaves water in it, he takes like a fork in it, has to pull it out,
Sorry.
and like it erupts with steam and water, and it's super cool.
Yeah.